All right, welcome to day 14. Homework is packet page 4. You can be doing that on a separate sheet of paper. So first one for our homework. Keep in mind our geometric series is the original term over 1 minus what we're multiplying by. So if you have 1 over 1 plus x, you're really starting with 1 and multiplying by negative x each time. So start with 1 multiplied by negative x, and notice we get that last line there where we're multiplying 1 minus x plus x squared minus x cubed and so on. In 2, we're going to take our answer from problem 1, which was 1 over 1 plus x, and its antiderivative would be the natural log of 1 plus x. Technically, there's a u substitution there, but du would just equal dx. There's no correction we have to do. Don't forget we have the plus c on the end. And we have to think about if we can resolve that plus c. Well, we know that natural log of 1 plus 0, so in other words, f of 0, which would give us natural log of 1, is just 0. So that means our c would be 0 in this case. So then just keep it out to the 5th degree, and that's our natural log of 1 plus x. So the second way that we can do it is we can take from today's class and we can put a negative x in. We had natural log of 1 plus x. So take what we had in class, put a negative x in, neaten it up, and notice it matches the same, our 5th degree polynomial. When you graph it, it's a pretty good match between negative 1 and 1. To get natural log of 0.8, we're really putting in negative 0.2 to natural log of 1 plus x. And then we would have 0.8 for 1.8 and then 4 for 5. So notice it's pretty close for the negative 0.2 and the 0.8, not really close at all for 4. And that goes with the idea that our Taylor polynomials, they are good approximations near the center. As you move further away from the center, it is not as good of an approximation. And these were our Maclaurin polynomials, so our center was at 0. So notice the negative 0.2 is closest to our center. That's why that's the best approximation. 0.8 a little further away, not as good. 4 is really far away, not good at all. So when we have our infinite geometric sum, we need that first thing in the denominator to be a 1. So to make that 2 be a 1, we had to multiply everything by a half. So that now gives us 5 halves over 1 minus x over 2, or 1/2 x. So you're starting with 5 halves and multiplying by x over 2 each time, and then just neaten it up, we get our 3rd degree polynomial. In the next one, think of it as you're starting with 3 and multiplying by negative x squared each time. So when you multiply that out, then just cut it off at our 4th degree. In C, we're starting with 2x and multiplying by negative x squared each time. This didn't go with that. So we're starting with 2x and multiplying by negative x squared each time. Neaten that up, and you've got your 5th degree term. In D, we've got to multiply by 1/2 again. So we get x over 2 as the first term, and you're multiplying by x over 2 every time. Neaten it up and stop once you get the 3rd degree. In 4, we're going to figure out for arctan, a Maclaurin polynomial. So we're going to start with, from problem 1, what we had for 1 over 1 plus x squared. Or sorry, to develop 1 over 1 plus x squared. So what we can do is we can just take an x squared and sub it in everywhere for x. Well, in B, your antiderivative of 1 over 1 plus x squared will give us arctan. So do that integral. We have a plus c, but because arctan of 0 is 0, we would need that c to be 0 to match up. So then we get our 5th degree polynomial there. Adding to your study card for arctan is a good one to put down. So we know arctan of x, our Maclaurin for that is x minus, and you can either write it as 1/3 x cubed, or you can write it as x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, dot, dot, dot. Okay, because that is a little bit of a pain to derive from your 1 over 1 minus x originally, which is a nice one we have. So that might be one that would be helpful to memorize. When you graph your polynomial in arctan, notice pretty close from -1 to 1, and a similar idea to the last one. When we're close to our center, it's a pretty good approximation. As you move further away, it is not as good of an approximation. In 5, we wanted to take our 1 over 1 minus x, which is just starting with 1 and multiplying by x, and then do our derivative, and that would be the same as 1 over 1 minus x squared. So just take that derivative. The first term goes away, and then you have 1 plus 2x plus 3x squared, and so on. And we wanted to cut it off at the third degree. And our last one, we just want to sub x squared into our one from number 2 to get natural log of 1 plus x squared. When you do that, neaten up and cut off at the 8th degree. And there's our graph of it. Notice close to the center, it's matching pretty well. So recall from the last class, we learned how to build a Maclaurin polynomial using our derivatives. And down in the bottom of this slide here is the key thing. So it's our y value at x equals 0 over 0 factorial, plus our first derivative at x equals 0 over 1 factorial times x to the first. And then second derivative over x squared, or over 2 factorial times x squared, and then so on for third derivative, and out to whatever degree we need. Well, on the bottom of this page, suppose that our center is not 0. Suppose it's x equals a. Well, there's two small things that happen. Notice our values of our function and each of our derivatives are now the value at x equals whatever our center is. And the other thing is, notice instead of x, we have x minus whatever our center is. So essentially it's shifted, because a minus on the inside would shift it right. Okay, if a happens to be negative, it would then shift it left. But it's x minus our center. Other than that, it's a pretty similar idea. And here's just that written out in general. So for any Taylor polynomial centered at x equals a, we can basically do the same thing that we did yesterday at the end of the class, but just with a few slight changes. So we're going to find a third degree Maclaurin for e to the x and use it to evaluate square root of e. So third degree, we need out to the third derivative. So I'm going to write it as f of x instead of y. So we have f of x is e to the x. Well, nicely, f prime of x is e to the x. Big surprise, f double prime of x is e to the x. And spoiler alert, f triple prime of x is e to the x. So we need to find those each at 0 because that's where our center is. We have a Maclaurin. So f of 0 is going to be 1. F prime of 0 is going to be 1. F double prime of 0 is going to be 1. And f triple prime of 0 is going to be 1. So that might seem redundant, but I just wanted to kind of show you through the process that you would want to do for that. So now for our third degree Taylor polynomial. We do our y value of the function at our center over 0 factorial. Then we'll do our value of our first derivative at the center over 1 factorial. And then it's x minus our center. So in this case, we have x minus 0, so we just have x. So then we'll do the value of our second derivative over 2 factorial. X minus our center squared, so in this case, Maclaurin, so we have x squared. And then we have our third derivative over 3 factorial, and then we'll have x cubed. We want to use this to evaluate e to the 1 square root of e, which is e to the 1/2. So we're going to do p3 of a half. And if we subbed in a half for this and put this in the calculator, we would get 1.6458 and then 3 repeating. Well, if you actually did e to the 1/2, you would get 1.64872. So reasonably close estimate of that. And if you go to the next page, you can see we're matching exactly at our center. As we move further away, the approximations for our polynomial are not as good. If we wanted them to become better, we could add more terms. So we just created a relationship between factorials and the value of e. Because our polynomial here, this one here, if we had wanted to find just e, that would be e to the first. So we would just put in 1 for all of the x's. When you put in 1 for the x's, you just have 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. So way, way back in the old days, even when you didn't have calculators or computers, you could calculate e pretty accurately just by doing some factorials, which are just multiplication. And here is that out to the 5th term, so it converges pretty quickly to e. So we're going to find a 3rd degree Taylor polynomial for sine x. We're centered at 2 pi over 3. So that means we're going to need 3 derivatives. So I guess actually before the derivative, let's just write f of x. F of x is sine x. F prime of x is cos x. F double prime of x, we have negative sine x. And f triple prime of x, we have negative cos x. Well, 2 pi over 3 is 120 degrees. So we need to think second quadrant, 60-degree reference angle. Opposite would be square root of 3, adjacent would be negative 1, and hypotenuse would be 2. So f of 2 pi over 3, we're looking for the sine, that would be square root of 3 over 2. F prime of 2 pi over 3, we're looking for the cos, that would be negative 1/2. Second derivative of 2 pi over 3 will be the negation of the sine, so we'll have negative square root of 3 over 2. And then lastly, third derivative at 2 pi over 3 would be the negation of the cos, so we get 1/2. So to write out our 3rd degree Taylor polynomial, we would have P3 of x is equal to our function value over 0 factorial plus our first derivative value over 1 factorial. We'll have x minus our center, and we're raised to the first. Then we'll have minus square root of 3 over 2 factorial. We'll have x minus 2 pi over 3. This is now raised to the second. And then we got to go one more for our 3rd degree, so we'll have plus 1/2 over 3 factorial. This will be x minus 2 pi over 3 raised to the 3rd. So, free response question, you could leave it right like that if you wanted. Okay, or you can neaten it up. The neatened up form, we'd have square root of 3 over 2 minus 1/2 x minus 2 pi over 3. 2 factorial is a 2, so when you divide by 2, we'd end up getting minus square root of 3 over 4, x minus 2 pi over 3 squared. 3 factorial 6, so this would become 1/12 x minus 2 pi over 3 to the 4th. And we wanted to approximate sine of 1.5. So P3 of 1.5. If we sub that into our polynomial, we would get 0.9927369 and some other stuff. So if we go down the bottom, here's a table. The first column there, the P3 of x is our polynomial. The second one is sine, and then I put in the error, how much it's off by. So notice at our center of 2 pi over 3, they match exactly. Because at your center, the function in the polynomial, as well as all their derivatives, will match up exactly. As you move further away from 2 pi over 3, it is not as good of an approximator. Now 2 pi over 3 is about 2.09 or so. So you can see it'll kind of be in that range of pretty close. That's it for this video. Enjoy the rest of your day.